What's going on? So, I have been recently really interested in this field of mechanistic interpretability, and I found out about this guy, Neel Nanda, from watching him on Machine Learning Street Talk podcast. And he has this list of recommended papers in order to get into the field. So, I'm just going to step through some of the papers, hopefully, as many as I can get through. And I might read certain parts deeply, I might just skim over certain parts, I'm not quite sure yet, but this is just going to be a little read along. And I also am going to start off by actually reading everything out by myself, but for certain parts, I might just use Speechify to have an AI read it to me. I'm not quite sure how it's going to go down, but we're going to start with what he considers the foundational work for mechanistic interpretability, which is this paper, A Mathematical Framework for Transformer Circuits by Anthropic. So to start out, transformer language models are an emerging technology that is gaining increasingly broad real-world use, for example in systems like GPT-3, Lambda, Codex, Mina, Gopher, and similar models. However, as these models scale, their open-endedness and high capacity creates an increasing scope for unexpected and sometimes harmful behaviors. Even years after a large model is trained, both creators and users routinely discover model capabilities, including problematic behaviors they were previously unaware of. One avenue for addressing these issues is mechanistic interpretability, attempting to reverse engineer the detailed computations performed by transformers, similar to how a programmer might try to reverse engineer complicated binaries into human-readable source code. If this were possible, it could potentially provide a more systematic approach to explaining current safety problems, identifying new ones, and perhaps even anticipating the safety problems of powerful feature models that have not yet been built. A previous project, the Distill Circuits thread, has attempted to reverse engineer vision models, but so far there hasn't been a comparable project for transformers or language models. In this paper, we attempt to take initial, very preliminary steps towards reverse engineering transformers. Given the incredible complexity and size of modern language models, we have found it most fruitful to start with the simplest possible models and work our way up from there. Our aim is to discover simple algorithmic patterns, motifs, or frameworks that can subsequently be applied to larger and more complex models. Specifically in this paper, we will study transformers with 2 layers or less, which have only attention blocks. This is in contrast to a large, modern transformer like GPT-3, which has 96 layers and alternates attention blocks with MLP blocks. We find that by conceptualizing this operation of transformers in a new but mathematically equivalent way, we are able to make sense of these small models and gain significant understanding of how they operate internally. Of particular note, we find that specific attention heads that we term induction heads can explain in-context learning in these small models, and that these heads only develop in models with at least 2 attention layers. So again, we find that specific attention heads that we term induction heads can explain in-context learning in these small models, and that these heads only develop in models with at least 2 attention layers. We also go through some examples of these heads operating in action on specific data. We don't attempt to apply to our insights. We don't attempt to apply to our insights to, we don't attempt to apply our insights to larger models in this first paper, but in a forthcoming paper, which is in context learning and induction heads, we will show that both our mathematical framework for understanding transformers and the concept of induction heads continues to be at least partially relevant for much larger and more realistic models, though we remain a very long way from being able to fully reverse engineer such models. Summary of results. Reverse engineering results. To explore the challenge of reverse engineering transformers, we reverse engineer several toy attention-only models. In doing so, we find 0-layer transformers model bigram statistics. The bigram table can be accessed directly from the weights. 1-layer attention-only transformers are an ensemble of bigram and skip trigram sequences of the form A to B, C models. The bigram and skip trigram tables can be accessed directly from the weights without running the model. These skip trigrams can be surprisingly expressive. This includes implementing a kind of very simple in-context learning. 2-layer attention-only transformers can implement much more complex algorithms using compositions of attention heads. These compositional algorithms can also be detected directly from the weights. Notably, two-layer models use attention head composition to create induction heads, a very general in-context learning algorithm. One-layer and two-layer attention-only transformers use very different algorithms to perform in-context learning. Two-layer attention heads use qualitatively more sophisticated inference time algorithms, in particular, a special type of attention head we call an induction head, to perform in-context learning, forming an important transition point that will be relevant for larger models. Okay, so apologies to a viewer, but I'm just going to take a quick note, and I'll probably be taking occasional notes throughout. Okay, enough notes. Conceptual takeaways. We found that many subtle details of the transformer architecture require us to approach reverse engineering it in a pretty different way from how the Inception V1 circuits work. We'll unpack each of these points in the sections below, but for now we briefly summarize. We'll also expand on a lot of the terminology we introduce here once we get to the appropriate sections. To be clear, we don't intend to claim that any of these points are necessarily novel. Many are implicitly or explicitly present in our other papers. Attention heads can be understood as independent operations, each outputting a result which is added into the residual stream. Attention heads are often described in an alternate concatenate and multiply formulation for computational efficiency, but this is mathematically equivalent. Attention-only models can be written as a sum of interpretable end-to-end functions, mapping tokens to changes in logits. These functions correspond to paths through the model and are linear if one freezes the attention patterns. Transformers have an enormous amount of linear structure. One can learn a lot simply by breaking apart sums and multiplying together chains of matrices. Attention heads can be understood as having two largely independent computations, a query key circuit, which computes the attention pattern, and an output value circuit, which computes how each token affects the output if attended to. Key query and value vectors can be thought of as intermediate results in the computation of the low-rank matrices WQ transpose, WK, and WO, WV. It can be useful to describe transformers without reference to them. Composition of attention heads greatly increases the expressivity of transformers. There are three different ways attention heads can compose, corresponding to keys, queries, and values. Key and query composition are very different from value composition. All components of a transformer, the token embedding, attention heads, MLP layers, and unembedding, communicate with each other by reading and writing to different subspaces of the residual stream. Rather than analyze the residual stream vectors, it can be helpful to decompose the residual stream into all these different communication channels corresponding to paths through the model. Transformer overview. Before we attempt to reverse engineer transformers, it's helpful to briefly review the high-level structure of transformers and describe how we think about them. In many cases, we found it helpful to reframe transformers in equivalent but non-standard ways. Mechanistic interpretability requires us to break models down into human interpretable pieces. An important first step is finding the representation which makes it easiest to reason about the model. In modern deep learning, there is, for good reason, a lot of emphasis on computational efficiency, and our mathematical descriptions of models often mirror decisions in how one would write efficient code to run the model. But when there are many equivalent ways to represent the same computation, it is likely that the most human interpretable representation and the most computationally efficient representation will be different. Reviewing transformers will also let us align on terminology, which can sometimes vary. We'll also introduce some notation in the process, but since this notation is used across many sections, we provide a detailed description of all notation in the notation appendix as a concise reference for readers. Model simplifications. To demonstrate the ideas in this paper in their cleanest form, we focus on toy transformers, with some simplifications. In most parts of this paper, we will make a very substantive change. We focus on attention-only transformers, which don't have MLP layers. This is a very dramatic simplification of the transformer architecture. We're partly motivated by the fact that circuits with attention heads present new challenges not faced by the distilled circuits work, and considering them in isolation allows us to give an especially elegant treatment of those issues. But we've also simply had much less success in understanding MLP layers so far. In normal transformers with both attention and MLP layers, there are many circuits mediated primarily by attention heads which we can study, some of which seem very important, but the MLP portions have been much harder to get traction on. This is a major weakness of our work that we plan to focus on addressing in the future. Despite this, we will have some discussion of transformers with MLP layers in later sections. We also make several changes that we consider to be more superficial and are mostly made for clarity and simplicity. We do not consider biases, but a model with biases can always be simulated without them by folding them into the weights and creating a dimension that is always 1. Additionally, biases in attention-only transformers mostly multiply out to functionally be biases on the logits. We also ignore layer normalization. It adds a fair amount of complexity to consider explicitly, and up to a variable scaling, layer norm can be merged into adjacent weights. We also expect that, modulo some implementational annoyances, layer norm could be substituted for batch normalization, which can fully be folded into adjacent parameters. High-level architecture. There are several variants of transformer language models. We focus on autoregressive, decoder-only transformer language models, such as GPT-3. The original transformer paper had a special encoder-decoder structure to support translation, but many modern language models don't include this. A transformer starts with a token embedding, followed by a series of residual blocks, and finally a token unembedding. Each residual block consists of an attention layer, followed by an MLP layer. Both the attention and MLP layers each read their input from the residual stream by performing a linear projection, and then write their results to the residual stream by adding a linear projection back in. Each attention layer consists of multiple heads which operate in parallel. So here, from bottom to top, you put the tokens in, you embed the tokens with x naught equals WET. So you're just multiplying the tokens by the weights, and then these enter the residual stream, where each attention head H is run and added to the residual stream. Let me just move this. I don't want to delete that, but I'll just move it out the way for now. So you can see that this right here, all of this is one residual block. And again, each attention head H is run and added to the residual stream. Xi plus 1 equals Xi plus the sum for the attention heads H of Xi. And then Xi plus 1 goes here, and MLP layer M is run and added to the residual stream. Xi plus 2 equals Xi plus 1 plus M of Xi plus 1. And then Xi plus 1 comes out and gets unembedded. Well, all of them, up Xi plus 1, Xi plus 2 up to X minus 1, so the last token. And then it gets unembedded. The final logits are produced by applying the unembedding. Big T of T equals WU X minus 1. Virtual weights and the residual stream as a communication channel. One of the main features of the high-level architecture of a transformer is that each layer adds its results into what we call the residual stream. The residual stream is simply the sum of the output of all the previous layers and the original embedding. We generally think of the residual stream as a communication channel, since it doesn't do any processing itself and all layers communicate through it. The residual stream has a deeply linear structure. Every layer performs an arbitrary linear transformation to read in information from the residual stream at the start, and performs another arbitrary linear transformation before adding to write its output back into the residual stream. I'm going to repeat that. The residual stream has a deeply linear structure. Every layer performs an arbitrary linear transformation to read in information from the residual stream at the start. Every layer performs an arbitrary linear transformation to read in information from the residual stream at the start, and performs another arbitrary linear transformation before adding to write its output back into the residual stream. This linear additive structure of the residual stream has a lot of important implications. One basic consequence is that the residual stream doesn't have a privileged basis. We could rotate it by rotating all the matrices interacting with it without changing model behavior. Virtual weights. An especially useful consequence of the residual stream being linear is that one can think of implicit virtual weights directly connecting any pair of layers, even those separated by many other layers, by multiplying out their interactions through the residual stream. These virtual weights are the product of the output weights of one layer with the input weights of another, i.e. Wi2, Wo1, and describe the extent to which a later layer reads in the information written by a previous layer. So here we see the weights of the input, and you get the weights of the output added back to the residual stream. Each layer reads from the residual stream from a linear projection. Here we see the weights of input 2 going here and coming out with the weights of output 2 back into the residual stream. Each layer writes to the residual stream by adding a linear projection of its results, and so on. The residual stream is modified by a sequence of MLP and attention layers reading from and writing to it with linear operations. Because all these operations are linear, we can multiply through the residual stream. So, alright, I'm just going to get rid of this. So here we see, by using different subspaces of the residual stream, a layer can send different information to different layers, or even not interact with other layers. So here you see weights input 3, weights output 1, and weights input 3, weights output 2, coming here. Multiplying out the weights reveals virtual weights implicitly connecting each pair of layers. And because all these operations are linear, we can multiply through the residual stream. Subspaces and residual stream bandwidth. The residual stream is a high-dimensional vector space. In small models, it may be hundreds of dimensions. In large models, it can go into the tens of thousands. This means that layers can send different information to different layers by storing it in different subspaces. This is especially important in the case of attention heads, since every individual head operates on comparatively small subspaces, often 64 or 128 dimensions, and can very easily write to completely disjoint subspaces and not interact. Once added, information persists in a subspace unless another layer actively deletes it. From this perspective, dimensions of the residual stream become something like memory or bandwidth. The original token embeddings, as well as the unembeddings, mostly interact with a relatively small fraction of the dimensions. Again, one second. Once added, information persists in a subspace unless another layer actively deletes it. From this perspective, dimensions of the residual stream become something like memory or bandwidth. The original token embeddings, as well as the unembeddings, mostly interact with a relatively small fraction of the dimensions. This leaves most dimensions free for other layers to store information in. It seems like we should expect residual stream bandwidth to be in very high demand. There are generally far more computational dimensions, such as neurons and attention head result dimensions, than the residual stream has dimensions to move information. Just a single MLP layer typically has 4 times more neurons than the residual stream has dimensions. So, for example, at layer 25 of a 50-layer transformer, the residual stream has 100 times more neurons as it has dimensions before it, trying to communicate with 100 times as many neurons as it has dimensions after it, somehow communicating in superposition. We call tensors like this bottleneck activations and expect them to be unusually challenging to interpret. This is a major reason why we will try to pull apart the different streams of communication happening through the residual stream apart in terms of virtual weights rather than studying it directly. Perhaps because of this high demand on residual stream bandwidth, we've seen hints that some MLP neurons and attention heads may perform a kind of memory management role, clearing residual stream dimensions set by other layers by reading in information and writing out the negative version. So here we see the residual stream is high dimensional and can be divided into different subspaces. So you have this layer going into the residual stream subspace, going back out into another layer. Layers can interact by writing to and reading from the same or overlapping subspaces. If they write to and read from disjoint subspaces, they won't interact. Typically, the spaces only partially overlap. And here we see coming out of the residual stream subspace into a layer and back in. Layers can delete information from the residual stream by reading in a subspace and then writing the negative version. I see. Attention heads are independent and additive. As seen above, we think of transformer attention layers as several completely independent attention heads, small h within big H, which operate completely in parallel and each add their output back into the residual stream. But this isn't how transformer layers are typically presented, and it may not be obvious they're equivalent. In the original Vaswani et al. Paper on transformers, the output of an attention layer is described by stacking the result vectors RH1, RH2, and then multiplying, so just to be clear, result from H1, result from H2, and then multiplying by an output matrix, WOH. Let's split WOH into equal size blocks for each head. So the weight matrix output H1, the weight matrix output H2. Then we observe that W output H, RH1, RH2, and so on equals W output H1, W output H2 times R H1, RH2 equals the sum for all I of W output HI, R, HI, revealing it to be equivalent to running heads independently, multiplying each by its own output matrix and adding them into the residual stream. The concatenate definition is often preferred because it produces a larger and more compute-efficient matrix multiply. But for understanding transformers theoretically, we prefer to think of them as independently additive. Attention heads as information movement. But if attention heads act independently, what do they do? The fundamental action of attention heads is moving information. Fundamental action of attention heads is moving information. They read information from the residual stream of one token and write it to the residual stream of another token. The main observation to take away from this section is that which tokens to move information from is completely separable from what information is read to be moved and how it is written to the destination. So here we say token A residual stream, token B residual stream. Attention heads copy information from the residual stream of one token to the residual stream of another. They typically write to a different subspace than they read from. To see this, it's helpful to write attention in a non-standard way. Given an attention pattern, computing the output of an attention head is typically described in 3 steps. 1. Compute the value vector for each token from the residual stream. Value I equals W V X I. Compute the result vector by linearly combining value vectors according to the attention pattern. Result I equals the sum for all j, aij, vj. Finally, compute the output vector of the head for each token. H of x I equals WORI. Each of these steps can be written as matrix multiply. Why don't we collapse them into a single step? If you think of X as a 2D matrix consisting of a vector for each token, we're multiplying it on different sides. WV and WO multiply the vector per token side, while A multiplies the position side. Tensors can offer us a much more natural language for describing this kind of map between matrices. If tensor product notation isn't familiar, we've included a short introduction in the notation appendix. One piece of motivation that may be helpful is to note that we want to express linear maps from matrices to matrices. So here we see n context, d model, maps to n context, d model. Mathematicians call such linear maps 2 by 2 tensors. They map 2 input dimensions to 2 output dimensions. And so tensors are the natural language for expressing this transformation. Again, mathematicians call such linear maps 2 tensors. They map 2 input dimensions to 2 output dimensions. And so tensors are the natural language for expressing this transformation. Using tensor products, we can describe the process of applying attention as h of x equals id times wo. I believe that's times, right? 1 second. Yeah, the tensor product. So this expression is pronounced identity tensor WO or identity. No, I'm not saying that. So ID is the identity matrix. This is the tensor product. And this is WO. Okay. So h of x equals identity tensor WO. Project result vectors out for each token. H of xi equals WORI dot attention identity. Mix value vectors across tokens to compute result vectors. Ri equals sum for all j, aij, vj dot identity wv. Compute value vector for each token. Vi equals wvxi dot x. Applying the mixed product property and collapsing identities yields h of x equals the product of a and wo wv dot x. A mixes across tokens while wo wv acts on each vector independently. What about the attention pattern? Typically, one computes the keys ki equals wk xi, computes the queries qi equals wq xi, and then computes the attention pattern from the dot products of each key and query vector a equals softmax q transpose k. But we can do it all in one step without referring to keys and queries. A equals softmax x transpose wq transpose wkx. It's worth noting that although this formulation is mathematically equivalent, actually implementing attention this way, i.e. multiplying by WOWV and WQ transpose WK, would be horribly inefficient. Observations about attention heads. A major benefit of rewriting attention heads in this form is that it surfaces a lot of structure which may have previously been harder to observe. Attention heads move information from the residual stream of one token to another. A corollary of this is that the residual stream vector space, which is often interpreted as a contextual word embedding, will generally have linear subspaces corresponding to information copied from other tokens and not directly about the present token. An attention head is really applying two linear operations, A and WOWV, which operate on different dimensions and act independently. A governs which token's information is moved from and to. WOWV governs which information is read from the source token and how it is written to the destination token. A is the only nonlinear part of this equation, being computed from a softmax. This means that if we fix the attention pattern, attention heads perform a linear operation. This also means that, without fixing A, attention heads are half-linear in some sense, since the per-token linear operation is constant. WQ and WK always operate together. They're never independent. Similarly, WO and WV always operate together as well. Although they're parameterized as separate matrices, WOWV and WQTWK can always be thought of as individual low-rank matrices. Keys, queries, and value vectors are, in some sense, superficial. They're intermediary byproducts of computing these low-rank matrices. One could easily reparameterize both factors of the low-rank matrices to create different vectors, but still function identically. I'm going to read that again. Keys, queries, and value vectors are, in some sense, superficial. They are intermediary byproducts of computing these low-rank matrices. One could easily reparameterize both factors of the low-rank matrices to create different vectors, but still function identically. Because WOWV and WQWK always operate together, we like to define variables representing these combined matrices. So WOV equals WOWV and WQK equals WQTWK. Products of attention heads behave much like attention heads themselves by the distributive property AH2 times WOVH2 dot AH1 times WOVH1 equals AH2 times AH1 times WOVH2 times WOVH1. The result of this product can be seen as functionally equivalent to an attention head with an attention pattern, which is the composition of the two heads AH2, AH1, and an output value matrix WOVH2, WOVH1. We call these virtual attention heads, discussed in more depth later. Zero-layer transformers. Before moving on to more complex models, it's useful to briefly consider a zero-layer transformer. Such a model takes a token, embeds it, unembeds it to produce logits predicting the next token. T equals WU, WE. So just the transformer is just our matrix of unembeds times the matrix of the embeddings. Because the model cannot move information from other tokens, we are simply predicting the next token from the present token. This means that the optimal behavior of WU, WE is to approximate the bigram log likelihood. This is relevant to transformers more generally. Terms of the form WU, WE will occur in the expanded form of equations for every transformer corresponding to the direct path where a token embedding flows directly down the residual stream to the unembedding without going through any layers. The only thing it can affect is the bigram log likelihoods, since other aspects of the model will predict parts of the bigram log likelihood. It won't exactly represent bigram statistics in larger models, but it does represent a kind of residual. In particular, the WU-WE term seems to often help represent bigram statistics which aren't described by more general grammatical rules, such as the fact that Barack is often followed by Obama. One-layer attention-only transformers. We claim that one-layer attention-only transformers can be understood as an ensemble of a bigram model and several skip trigram models, affecting the probabilities of sequences A to BC. Intuitively, I'm just going to read from the start again. We claim that one-layer attention-only transformers can be understood as an ensemble of a bigram model and several skip trigram models. Intuitively, this is because each attention head can selectively attend from the present token B to a previous token A and copy information to adjust the probability of possible next tokens C. The goal of this section is to rigorously show this correspondence and demonstrate how to convert the raw weights of a transformer into interpretable tables of skip trigram probability adjustments. The path expansion trick. Recall that a one-layer attention-only transformer consists of a token embedding followed by an attention layer, which independently applies attention heads, and finally an unembedding. So again, token embedding. Each attention head H is run and added to the residual stream. The final logics are produced by applying the unembedding. Using tensor notation and the alternative representation of attention heads we previously derived, we can represent the transformer as a product of three terms. So the transformer equals the identity times WU. The token unembedding maps residual stream vectors to logits. We see the identity plus the sum for all H's in H1, AH times WOVH. The attention layer has multiple heads. The result of each is added into the residual stream times the identity times WE. The token embedding maps tokens to residual stream vectors, where AH equals softmax with autoregressive masking of TT plus WET WQKH WE times T. Attention pattern logits are produced by multiplying pairs of tokens through different sides of WQKH. Our key trick is to simply expand the product. This transforms the product, where every term corresponds to a layer, into a sum where every term corresponds to an end-to-end path. So T equals identity product WUWE. The direct path term contributes to bigram statistics, plus the sum for all H, AH, product WU, WOVH, WE. The attention head terms describe the effects of attention heads in linking input tokens to logits. AH describes which tokens are attended to, while WU, WOVH, WE describes how each token changes the logits if attended to. We claim each of these end-to-end path terms is tractable to understand, can be reasoned about independently, and additively combined to create model behavior. Again, we claim each of these end-to-end path terms is tractable to understand, can be reasoned about independently, and additively combined to create model behavior. Bold claim. The direct path term, ID product WUWE, also occurred when we looked at the zero-layer transformer because it doesn't move information between positions. That's what ID product denotes. The only thing it can contribute to is the bigram statistics, and it will fill in missing gaps that other terms don't handle there. The more interesting terms are the attention head terms. Splitting attention head terms into query key and output value circuits. For each attention head H, we have a term AH times WU, WOVH, WE, where AH equals a softmax of token T times WET, WQKH, WE times token. How can we map these terms to model behavior? And while we're at it, why do we get these particular products of matrices on our equations? The key thing to notice is that these terms consist of two separable operations, which are at their heart two and vocab matrices. WETWQKHWE. We call this matrix the query key QK circuit. It provides the attention score for every query and key token. That is, each entry describes how much a given query token wants to attend to a given key token. WU, WOVH, WE. We call this matrix the output value OV circuit. It describes how a given token will affect the output logits if attended to. Just going to make a quick note of this. Maybe not too quick. And the reason I say not too quick is because I have to type latex. Cool. Okay. To intuitively understand these products, it can be helpful to think of them as paths through the model, starting and ending at tokens. The QK, or query key circuit, is formed by tracing the computation of a query and key vector up to their attention head, where they dot product to create a bilinear form. The OV circuit is created by tracing the path, computing a value vector, and the output value circuit is created by tracing the path, computing a value vector, and continuing it through up to the logits. So here we see source, WE and WE, go to WV and WK. This goes to WQ, goes to WE. This goes to WO, WU. The output value circuit determines how attending to a given token affects the logits. The query key circuit controls which tokens the head prefers to attend to. The attention pattern is a function of both the source and destination token. But once a destination token has decided how much to attend to a source token, the effect on the output is solely a function of that source token. That is, if multiple destination tokens attend to the same source token the same amount, then the source token will have the same effect on the logits for the predicted output token. Output value and query key independence, the freezing attention patterns trick. Thinking of the output value and query key circuits separately can be very useful, since they're both individually functions we can understand. Linear or bilinear functions operating on matrices we understand. But is it really principled to think about them independently? One thought experiment which might be helpful is to imagine running the model twice. The first time you collect the attention patterns of each head. This only depends on the query key circuit. The second time, you replace the attention patterns with the frozen attention patterns you collected the first time. This gives you a function where the logits are a linear function of the tokens. We find this a very powerful way to think about transformers. Interpretation as skip trigrams. One of the core challenges of mechanistic interpretability is to make neural network parameters meaningful by contextualizing them. See discussion by Voss et al. On visualizing weights. Interesting. By multiplying out the output value and query key circuits, we've succeeded in doing this. The neural network parameters are now simple, linear, or bilinear functions on tokens. The query key circuit determines which source token the present destination token attends back to and copies information from, while the output value circuit describes what the resulting effect on the out predictions for the next token is. Together, the three tokens involved form a skip trigram of the form source, destination, out, and the out is modified. It's important to note that this doesn't mean that interpretation is trivial. For one thing, the resulting matrices are enormous. Our vocabulary is 50,000 tokens, so a single expanded output value matrix has 2.5 billion entries. We revealed the one-layer attention-only model to be a compressed Chinese room, and we're left with a giant pile of cards. There's also all the usual issues that come with understanding the weights of generalized linear models acting on correlated variables and fungibility between variables. For example, an attention head might have a weight of 0 because another attention head will attend to the same token and perform the same role it would have. I'm going to reread that. I'm going to read this whole paragraph. It's important to note that this doesn't mean that interpretation is trivial. For one thing, the resulting matrices are enormous. Our vocabulary is 50,000 tokens, so a single expanded output value matrix has 2.5 billion entries. We revealed the one-layer attention-only model to be a compressed Chinese room, and we're left with a giant pile of cards. There's also all the usual issues that come with understanding the weights of generalized linear models acting on correlated variables and fungibility between variables. For example, an attention head might have a weight of 0 because another attention head will attend to the same token and perform the same role it would have. Finally, there's a technical issue where query key weights aren't comparable between different query vectors, and there isn't a clear right answer as to how to normalize them. Despite this, we do have transformers in a form where all parameters are contextualized and understandable. And despite these subtleties, we can simply read off skip trigrams from the joint output vector and query key matrices. In particular, searching for large entries in these matrices reveals lots of interesting behavior. In the following subsections, we give a curated tour of some interesting skip trigrams and how they're embedded in the query key output value circuits, but full, non-cherry-picked examples of the largest entries in several models are available by following those links. Copying primitive in context learning. One of the most striking things about looking at these matrices is that most attention heads in one layer, maybe I should actually look at this, not this. So these are the queries that prefer the key. This is the key, and this is the effect on logits. So for example, turning and prefers turning, and turning affects the logits with heading, running, turning, love, ate, interesting, concern, hate. This is cool. Okay, zoom back in. Okay, copying, primitive in context learning. One of the most striking things about looking at these matrices is that most attention heads in one layer, models, dedicate an enormous fraction of their capacity to copying. The OV circuit, the output value circuit, sets things up so that tokens, if attended to by the head, increase the probability of that token, and to a lesser extent, similar tokens. The query key circuit then only attends back to tokens which could plausibly be the next token. Thus, tokens are copied, but only to places where bigram-ish statistics make them seem plausible. Some examples of large entries: query key output value circuit, source token perfect, destination token R looks is provides, out token perfect, super absolute pure, example skip trigrams perfect, R perfect, perfect looks super. In the above example, we fix a given source token and look at the largest corresponding query key entries, which is the destination token, and largest corresponding output value entries, the out token. The source token is selected to show interesting behavior, but the destination and out token are the top entries unless entries are explicitly skipped with an ellipsis. They are colored by the intensity of their value in the matrix. So perfect, give me 1 second to just read and think. So perfect is the source token. And we're looking at the destination token, which is the largest corresponding query key entries. So the largest corresponding query key entry for perfect, or the largest just query key entry for perfect, is R. That's the destination token. So the idea, I think, is if you see R, it's going to respond back to perfect, and the predicted output is going to be perfect, and you end up with a sequence akin to perfect dot 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 R perfect. In the example above, we fix a given source token. Okay, understood. Most of the examples are straightforward, but two deserve explanation. The fourth example with skip trigrams like lambda to $ backslash backslash lambda appears to be appears to be the model learning latex. While the fifth example with the skip trigram NBSP dot 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 to arrow ampersand NBSP appears to be the model learning HTML escape sequences. Note that most of these examples are copying. This appears to be very common. We also see more subtle kinds of copying. One particularly interesting one is related to how tokenization for transformers typically works. Tokenizers typically merge spaces onto the start of words, but occasionally a word will appear in a context where there isn't a space in front of it, such as at the start of a new paragraph or after a dialogue open quote. These cases are rare, and as such the tokenization isn't optimized for them. So for less common words, it's quite common for them to map to a single token when a space is in front of them. Space Ralph maps to space Ralph, but split when there isn't a space. Ralph maps to R Alf. It's quite common to see skip trigram entries dealing with copying in this case. In fact, we sometimes observe attention heads which appear to partially specialize in handling copying for words that split into two tokens without a space. When these attention heads observe a fragmented token, e.g. R, they attend back to tokens which might be the complete word with a space, space Ralph, and then predict the continuation alpha. It's really cool. It's interesting to note that this could be thought of as a very special case where a one-layer model can kind of mimic the induction heads we'll see in two-layer models. More examples of large entries: query key output value circuit. Our source token is Indy, the destination token is C, the output will be Indy, so you get Indy, Cindy. Here we see Pike, source token is Pike, destination token is P, output token is Ike, source token is Ralph, destination token is R, out token is Alf. Lloyd is the source token, destination token L, Pixmap, P, Xmap. We can summarize this copying behavior into a few abstract patterns we've noticed. Primitive in-context learning patterns. B.A maps to B. B.A, so B.A maps to B would be space 2, space 1 is going to map to 2. Space perfect, space R maps to space perfect. B.A maps to B prime, so space 2 space has maps to space 3. Space perfect looks maps to space super. AB A maps to B, so Ralph space R maps to Alf. Makes sense? AB A maps to B prime. Ralph space R maps to uppercase Alf. Pike space P maps to Ikes. All of these can be seen as a kind of very primitive in-context learning. The ability of transformers to adapt to their context is one of their most interesting properties, and this kind of simple copying is a very basic form of it. However, we'll see when we look at a two-layer transformer that a much more interesting and powerful algorithm for in-context learning is available to deeper transformers. Other interesting skip trigrams. Of course, copying isn't the only behavior these attention heads encode. Skip trigrams seem trivial, but can actually produce more complex behavior than one might expect. Below are some particularly striking skip trigram examples we found in looking through the largest entries in the expanded output value query key matrices of our models. Python. Predicting that the Python keywords else, elif, and except are more likely after an indentation is reduced using skip trigrams of the form new line, tab, 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 to new line, tab, tab, else elif, except, where the first part is indented n times and the second part n minus 1 for various values of n, where the white space can be tabs or spaces. Predicting that open will have a file mode string argument open something, comma, rb, wb, rw, for example, abc.txt, r. The first argument to a function is often self, def, self, for example, def method name, self. In Python 2, okay, these all make sense. One thing to note is that the learned skip trigrams are often related to idiosyncrasies of one's tokenization. For example, collapsing white space together allows individual tokens to reveal indentation. Collapsing white space together allows individual tokens to reveal indentation. Not merging backslash into text tokens means that when the model is predicting latex, there's a token after backslash that must be an escape sequence, and so on. Many skip trigrams can be difficult to interpret without specific knowledge, e.g., Israel to K, NES, only makes sense if you know Israel's legislative body is called the Knesset. A useful tactic can be to try typing potential skip trigrams into Google search or similar tools and look at auto-completions. Interesting. Primarily positional attention heads. Our treatment of attention heads hasn't discussed how attention heads handle position, largely because there are now several competing methods, e.g. 1, 13, 14, and they would complicate our equations. In the case of standard positional embeddings, The one-layer math works out to multiplying the query key weights by the positional embeddings. In practice, the one-layer models tend to have a small number of attention heads that are primarily positional, strongly preferring certain relative positions. Below, we present one attention head which either attends to the present token or the previous token. So here we see some examples. Source token is corresponding. Sorry. Destination token primarily positional. Out token to. Examples corresponding to, corresponding with, and so on. Skip trigram bugs. One of the most interesting things about looking at the expanded query key and output value matrices of one-layer transformers is that they can shed light on transformer behavior that seems incomprehensible from the outside. Our one-layer models represent skip trigrams in a factored form split between the output value and query key matrices. It's kind of like representing a function f of abc equals f1 ab, f2 ac. They can't really capture the three-way interactions flexibly. For example, if a single head increases the probability of both keep in mind and keep at bay, it must also increase the probability of keep in bay and keep at mind. This is likely a good trade for the model on balance, but is also, in some sense, a bug. We frequently observe these in attention heads. So pixmap, destination token P, out token xmap, correct skip trigrams, pixmap, bug skip trigrams, pixmap, canvas, or pcanvas. Highlighted text denotes skip trigram continuations that the model presumably ideally wouldn't increase the probability of. Note that qcanvas is a class involving pixmaps in the popular Qt library. Lloyd Catherine likely refers to Catherine Lloyd Burns. These examples are slightly cherry-picked to be interesting, but very common if you look at the expanded weights for models linked above. Even though these particular bugs seem in some sense trivial, we're excited about this result as an early demonstration of using interpretability to understand model failures. We have not further explored this phenomenon, but we'd be curious to do so in more detail. For instance, could we characterize how much performance, in points of loss or otherwise, these bugs are costing the model? Does this particular class continue to some extent in larger models, presumably partially but not completely masked by other effects? Summarizing output value query key matrices. We've turned the problem of understanding one-layer attention-only transformers into the problem of understanding their expanded output value and query key matrices. But as mentioned above, the expanded output value and query key matrices are enormous, with easily billions of entries. While searching for the largest entries is interesting, are there better ways to understand them? There are at least 3 reasons to expect there are. The output value and query key matrices are extremely low rank. They are 50,000 by 50,000 matrices, but only rank D head 64 or 128. In some sense, they're quite small even though they appear large in their expanded form. Looking at individual entries often reveals hints of much simpler structure. For example, we observe one head where names of people all have the top queries, like space by, e.g. and ... by maps to an, while location names have top queries like space from, e.g. Canada ... from maps to Canada. This hints at something like cluster structure in the matrix. Copying behavior is widespread in output value matrices, and arguably one of the most interesting behaviors. We'll see in the next section that there's analogous query key matrix structure in 2-layer models that's used to search for similar tokens to a query. It seems like it should be possible to formalize this. We don't yet feel like we have a clear right answer, but we're optimistic that the right kind of matrix decomposition or dimensionality reduction could be highly informative. See the technical details appendix for notes on how to efficiently work with these large matrices. Detecting copying behavior. The type of behavior we're most excited to detect in an automated way is copying. Since copying is fundamentally about mapping the same vector to itself, for example, having a token increase its own probability, it seems unusually amenable to being captured in some kind of summary statistic. However, we found it hard to pin down exactly what the right notion is. This is likely because there are lots of slightly different ways one could draw the boundaries of whether something is a copying matrix, and we're not yet sure what the most useful one is. For example, we don't observe this in the models discussed in this paper, but in slightly larger models, we often observe attention heads which copy some mixture of gender, plurality, and tense from nearby words, helping the model use the correct pronouns and conjugate verbs. The matrices for these attention heads aren't exactly copying individual tokens, but it seems like they are copying in some very meaningful sense. So copying is actually a more complex concept than it might first appear. One natural approach might be to use eigenvectors and eigenvalues. Recall that vector I is an eigenvector of the matrix M with an eigenvalue lambda I if MVI equals lambda I VI. Let's consider what that means for an output value circuit. M equals weights unembedding weights output value H weights embedding if lambda I is a positive real number. Then we're saying that there's a linear combination of tokens which increases the linear combination of logits of those same tokens. Perhaps all tokens representing plural words for a very broad one, or all tokens starting with a given first letter, or all tokens representing different capitalizations and inclusions of space for a single word for a narrow one, which mutually increase their own probability. For example, in general, we expect the eigenvectors have both positive and negative entries, so it's more like there are two sets of tokens, e.g. tokens representing male and female words, or tokens representing singular and plural words, which increase the probability of other tokens in the same set and decrease those in others. The eigendecomposition expresses the matrix as a set of such eigenvectors and eigenvalues. For a random matrix, we expect to have an equal number of positive and negative eigenvalues, and for many to be complex. But copying requires positive eigenvalues, and indeed we observe that many attention heads have positive eigenvalues, apparently mirroring the copying structure. Eigenvalue analysis of first layer attention head OV circuits. Non-positive eigenvalues, not copying heads. 10 out of 12 of layer 1 heads have mostly positive output value eigenvalues and appear to significantly perform copying. We use a log scale to represent magnitude since it varies by many orders of magnitude. Eigenvalue distribution for randomly initialized weights. Note that the mostly and in some cases entirely positive eigenvalues we observe are very different from what we randomly expect. One can even collapse that down further and get a histogram of how many of the attention heads are copying if one trusts the eigenvalues as a summary statistic. Histograms of attention heads, number of heads, the sum, lambda I, the sum of the absolute value, maybe the norm, lambda I. Histograms of attention heads by the fraction of their eigenvalues that are positive can be a useful summary. It appears that 10 out of 12 heads are significantly copying. This agrees with the qualitative inspection of the expanded weights. But while copying matrices must have positive eigenvalues, it isn't clear that all matrices with positive eigenvalues are things we necessarily want to consider to be copying. A matrix's eigenvectors aren't necessarily orthogonal, and this allows for pathological examples. For example, there can be matrices with all positive eigenvalues that actually map some tokens to decreasing the logits of that same token. Positive eigenvalues still mean that the matrix is, in some sense, copying on average, and there's still quite strong evidence of copying in that they seem improbable by default and empirically seem to align with copying, but they shouldn't be considered a dispositive proof that a matrix is copying in all senses one might reasonably mean. One might try to formalize copying matrices in other ways. One possibility is to look at the diagonal of a matrix, which describes how each token affects its own probability. As expected, entries on the diagonal are very positive leaning. We can also ask how often a random token increases its own probability more than any other token, or is one of the k most increased tokens to allow for tokens which are the same with a different capitalization or with a space. All of these seem to point in the direction of these attention heads being copying matrices, but it's not clear that any of them is a fully robust formalization of the primary behavior of this matrix is copying. It's worth noting that all of these potential notions of copying are linked by the fact that the sum of the eigenvalues is equal to the trace is equal to the sum. Okay, so it's worth noting that all of these potential notions of copying are linked by the fact that the sum of the eigenvalues is equal to the trace is equal to the sum of the diagonal. For the purposes of this paper, we'll continue to use the eigenvalue-based summary statistic. We don't think it's perfect, but it seems like quite strong evidence of copying and empirically aligns with manual inspection and other definitions. Do we fully understand one-layer models? There's often skepticism that it's even possible or worth trying to truly reverse engineer neural networks. That being the case, it's tempting to point at one-layer attention-only transformers and say, look, if we take the most simplified toy version of a transformer, at least that minimal version can be fully understood. But that claim really depends on what one means by fully understood. It seems to us that we now understand this simplified model in the same sense that one might look at the weights of a giant linear regression and understand it, or look at a large database and understand what it means to query it. That is a kind of misunderstanding. There's no longer any algorithmic mystery. The contextualization problem of neural network parameters has been stripped away. But without further work on summarizing it, there's far too much there for one to hold the model in their head. Given that regular one-layer neural networks are just generalized linear models and can be interpreted as such, perhaps it isn't surprising that a single attention layer is mostly one as well. Again, given that regular one-layer neural networks are just generalized linear models and can be interpreted as such, perhaps it isn't surprising that a single attention layer is mostly one as well. Two-layer attention-only transformers. Deep learning studies models that are deep, which is to say they have many layers. Empirically, such models are very powerful. Where does that power come from? One intuition might be that depth allows composition, which creates powerful expressiveness. Composition of attention heads is the key difference between one-layer and two-layer attention-only transformers. Without composition, a two-layer model would simply have more attention heads to implement skip trigrams with. But we'll see that in practice, two-layer models discover ways to exploit attention head composition to express a much more powerful mechanism for accomplishing in-context learning. In doing so, they become something much more like a computer program running an algorithm, rather than lookup tables of skip trigrams we saw in one-layer models. 3 kinds of composition. Recall that we think of the residual stream as a communication channel. Every attention head reads in subspaces of the residual stream determined by the query weights, the key weights, and the value weights, and then writes to some subspace determined by the output weights. Since the attention head vectors are much smaller than the size of the residual stream, typical values of d head divided by d model might vary from around 1/10 to 1/100. Attention heads operate on small subspaces and can easily avoid significant interaction. When attention heads do compose, there are 3 options. Q composition, where the query weights reads in a subspace affected by a previous head. K composition, where the key weights reads in a subspace affected by a previous head. And V composition, where the value weight matrix reads in a subspace affected by a previous head. Q and K composition are quite different from V composition. Q and K composition both affect the attention pattern, allowing attention heads to express much more complex patterns. V composition, on the other hand, affects what information an attention head moves when it attends to a given position. The result is that V-composed heads really act more like a single unit and can be thought of as creating an additional virtual attention heads. Composing movement of information with movement of information gives movement of information, whereas attention heads affecting attention patterns is not reducible in this way. To really understand these three kinds of composition, we'll need to study the output value and query key circuits again. Path expansion of logits. The most basic question we can ask of a transformer is, how are the logits computed? Following our approach to the one-layer model, we write out a product where every term is a layer in the model and expand to create a sum where every term is an end-to-end path through the model. So here we see the transformer equals product of the identity and the unembedding weight matrix times the identity plus the sum H within H2 of attention H product the output value weight matrix for that layer. The second attention layer has multiple attention heads, or sorry, it's fine. The second attention layer has multiple attention heads which add into the residual stream. And the product with the identity plus the sum for all the heads, attention H, product output value weights H. The first attention layer has multiple attention heads which add into the residual stream, and the product with the identity times the embedding weights, and all that is equal to the identity of the product, the unembedding weights with the embedding weights. Direct path term contributes to bigram statistics plus the sum for H within H1 union H2, AH, product unembedding weights, output value weights for that head, embedding weights. The individual attention head terms describe the effects of individual attention heads in linking input tokens to logits, similar to those we saw in the one-layer model, plus the sum H2 within H, and the sum of H1 within H1, AH2, AH1, product unembedding weights, output value weights for H2, output value weights for H1, embedding weights. The virtual attention head terms correspond to V composition of attention heads. They function a lot like individual attention heads with their own attention patterns, the composition of the heads patterns, and own output value matrix. Two of these terms, the direct path term and the individual head terms, are identical to the one-layer model. The final virtual attention head term corresponds to V composition. Virtual attention heads are conceptually very interesting, and we'll discuss them more later. However, in practice, we'll find that they tend to not play a significant role in small two-layer models. Path circuit expansion of attention scores, query key circuit. Just looking at the logit expansion misses what is probably the most radically different property of a two-layer attention-only transformer. Q composition and K composition cause them to have much more expressive second-layer attention patterns. To see this, we need to look at the query key circuits computing the attention patterns. Recall that the attention pattern for a head H is attention H equals softmax token T times C query key H T, where C query key H is the query key circuit mapping tokens to attention scores. For first layer attention heads, the query key circuit is just the same matrix we saw in the one-layer model. Query key circuit of head within H1 equals the embedding weights transpose the query key weights of H the embedding weights. But for the second layer query key circuit, both Q composition and K composition come into play, with previous layer attention heads potentially influencing the construction of the keys and queries. Ultimately, the query key weight acts on the residual stream. In the case of the first layer, this reduced to just acting on the token embeddings. So the query key circuit of H within H1 equals X naught T, weight query key H X naught equals embedding weights transpose query key weights of H with the embedding weights. But by the second layer, the query key circuit H within H2 equals X1T, query key weights H X1 is acting on X1, the residual stream after first layer attention heads. We can write this down as a product, with the first layer both on the key side and query side. Then we apply our path expansion trick to the product. One complicating factor is that we have to write it as a 6-dimensional tensor using 2 tensor products on matrices. This is because we're trying to express a multilinear function of the form n context d model times n context d model maps to n context n context. In the one layer case, we could sidestep this by implicitly doing an outer product, but that no longer works. A natural way to express this is as a 4x2 tensor, one with 4 input dimensions and 2 output dimensions. Each term will be of the form so query attention times the key attention times the weight matrix, where x of all that, y equals q, so aq t x w y a k, meaning that the query attention describes the movement of query side information between tokens. The key attention describes the movement of key side information between tokens, and the weight matrix describes how they product together to form an attention score. So query key circuit H in H2 equals identity, embedding weights T plus the sum for HQ within H1, AHQ, so the attention on the query on the head, product the identity, product output value weights HQ, weights, embedding weights, transpose. The query side residual stream at the start of the second layer contains both the layer 1 direct path and layer 1 attention heads. All terms are of the form product identity because they don't move key information. Identity, query key weights H. Query key weights of the second layer head combines both sides into attention scores. Identity, embedding weight plus sum HK within H1, identity, attention HK, output value weights HK, embedding weights. The key side residual stream at the start of the second layer contains both the layer 1 direct path and attention heads. All terms are of the form identity product because they don't move query information. Equals identity, embedding weights T, query key weights H, embedding weights. The no composition term, both first layer follows the direct path on both the key and query side, plus the sum of HQ within H1, attention HQ, ID, EWT, output value weights, HQ, T, query key weights, H, embedding weights. These terms correspond to pure Q composition. A previous attention head is used to generate the query side, but the key side is the first layer direct path, plus the sum for key heads within H1, identity, attention on the keys in H, or HK, product, embedding weights, query key weights of H, output value weights of HK, embedding weights. These terms correspond to pure K composition. A previous attention head is used to generate part of the key, but the query side is the first layer direct path, plus the sum for HQ within H1, and the sum for HK within H1, attention HQ, product, attention HK, product, embedding weights, output value weights HQ, query key weights H, output value weights HK, embedding weights. These terms are interactions between both Q composition and K composition. A previous attention head is used to generate the query and key sides. Each of these terms corresponds to a way the model can implement more complex attention patterns. In the abstract, it can be hard to reason about them, but we will return to them with a concrete case shortly when we talk about induction heads. Analyzing a two-layer model. So far, we've developed a theoretical model for understanding two-layer attention-only models. We have an overall equation describing the logits, the output value circuit, and then an equation describing how each attention head's attention pattern is computed, the query key circuit. But how do we understand them in practice? In this section, we'll reverse engineer a single two-layer model. Recall that the key difference between a two-layer model and a one-layer model is Q, K, and V composition. Without composition, the model is just a one-layer model with extra heads. Small two-layer models seem to often, though not always, have a very simple structure of composition, where the only type of composition is K composition between a single first-layer head and some of the second-layer heads. The following diagram shows Q, K, and V composition between first and second layer heads in the model we wish to analyze. We've colored the heads involved by our understanding of their behavior. The first layer head has a very simple attention pattern. It primarily attends to the previous token, and to a lesser extent the present token and the token 2 back. The second layer heads are what we call induction heads. Correction. The following diagram has an error introduced by a bug in an underlying library we wrote to accelerate linear algebra on low-rank matrices. A detailed comment on this, along with the corrected figure, can be found below. Well, what's the corrected figure at least? So this was the original plot. See, these are activated in Q composition. And you can't really make out some of the, or I guess it's just weaker connections. Induction heads, previous token heads. Note line widths between original and corrected plots are not directly comparable. Okay. Okay, bring me back. Here, okay. The above diagram shows Q, K, and V composition between attention heads in the first and second layer. That is, how much does the query key or value vector of a second layer head read in information from a given first layer head? This is measured by looking at the Frobenius norm of the product of the relevant matrices, divided by the norms of the individual matrices. For Q composition, query key weights H2, output value weights H1, the norm of the Frobenius norm, divided by query key weights H2, the Frobenius norm of that, and the Frobenius norm of the output value weights H1. For K composition, query key weights H2, output value weights H1's norm, divided by query key weights H2's norm times output value weights H1's norm. For V composition, and output value weights H2, output value weights H1's norm, divided by the product of the output value weights H2's norm and the output value weights H1's norm. By default, we subtract off the empirical expected amount for random matrices of the same shapes. Most attention heads have a much smaller composition than random matrices. In practice, for this model, there is only significant K composition and only with one layer 0 head. One quick observation from this is that most attention heads are not involved in any substantive composition. We can think of them as roughly a larger collection of skipped trigrams. This two-layer model has a mystery for us to figure out, but it's a fairly narrowly scoped one. We speculate this means that having a couple induction heads, in some sense, outcompetes a few potential skip trigram heads, but no other type of composition did. That is, having more skip trigram heads is a competitive use of second layer attention heads in a small model. In the next few sections, we'll develop a theory of what's going on, but before we do, we provide an opportunity to poke around at the attention heads using the interactive diagram below, which displays value-weighted attention patterns over the first paragraph of Harry Potter and the Philosopher's Stone. We've colored the attention heads involved in K composition using the same scheme as above. This makes it a bit hard to investigate the other heads. If you want to look at those, an interface for general explanation or exploration is available here. Where'd that go? Okay, I'll look at that later. But back here, we recommend isolating individual heads and both looking at the pattern and hovering over tokens. For induction heads, note especially the off-diagonal lines in the attention pattern and the behavior on the tokens compositing Dursley and Potters. So here, attention heads 0, 0, it's nothing. Move to 0, 1, doesn't really pick up, so till here, which represents layer 0 heads. Okay, this makes sense. And ders and run and ters. Start, Mr. and so you're seeing where the attention is focused at each token. So the expectation is that when you go to this Dursley down here, you're seeing it's very much activated by this previous example. And this is, the ers is noticing the Lee, and so it's predicting Lee. And that's got attention here. It's funny how many times Dursley is in here. I've never actually, well, no, I've definitely read this book when I was like a little kid, but I forget it. And I doubt that I made it through the whole thing. Maybe I did, I don't know. Mr. and Mrs. Dursley of number 4 private drive are proud to say that they were perfectly normal. Thank you very much. Alright, but moving on. So let's read this. The above diagram shows the value-weighted attention patterns for various attention heads. That is, the attention patterns with attention weights scaled by the norm of the value vector at the source position, source vector h, or the value vector at the source, okay, source v h. You can think of the value-weighted attention pattern as showing how big a vector is moved from each position. This approach was also recently introduced by Kobayashi et al. This is especially useful because attention heads will sometimes use certain tokens as a kind of default or resting position when there isn't a token that matches what they're looking for. The value vector at these default positions will be small, and so the value-weighted pattern is more informative. The interface allows one to isolate attention heads, shows the overall attention pattern, and allows one to explore the attention for individual tokens. Attention heads involved in K composition are colored using the same scheme as above. We suggest trying to isolate these heads. If you look carefully, you'll notice that the aqua-colored induction heads often attend back to previous instances of the token which will come next. We'll investigate this more in the next section. Of course, looking at attention patterns on a single piece of text, especially a well-known paragraph like this one, can't give us very high confidence as to how these heads behave in generality. We'll return to this later once we have a stronger hypothesis of what's going on. Induction heads. In small two-layer attention-only transformers, composition seems to be primarily used for one purpose, the creation of what we call induction heads. We previously saw that the one-layer model dedicated a lot of its capacity to copying heads as a crude way to implement in-context learning. Induction heads are a much more powerful mechanism for achieving in-context learning. We will explore the role of induction heads in in-context learning in more detail in our next paper. Function of induction heads. If you played around with the attention patterns above, you may have already guessed what induction heads do. Induction heads search over the context for previous examples of the present token. If they don't find it, they attend to the first token, in our case, a special token placed at the start, and do nothing. But if they do find it, then they look at the next token and copy it. This allows them to repeat previous sequences of tokens both exactly and approximately. It's useful to compare induction heads to the types of in-context learning we observed in one-layer models. One-layer model copying head, B to A maps to B, and when rare quirks of tokenization allow AB to A maps to B. Two-layer model induction head, A, B to A maps to B. The two-layer algorithm is more powerful. Rather than generically looking for places it might be able to repeat a token, it knows how the token was previously used and looks out for similar cases. This allows it to make much more confident predictions in those cases. It's also less vulnerable to distributional shift, since it doesn't depend on learned statistics about whether one token can plausibly follow another. We'll see later that induction heads can operate on repeated sequences of completely random tokens. The following examples highlight a few cases where induction heads help predict tokens in the first paragraph of Harry Potter. So we see Mr. and Mrs. Dursley of such nonsense. Mr. Dursley was the and so the attention is on and. So okay, I see. Nonsense is the present token. The attention is on the beginning. Same for period. At Mr., the attention gets placed on and weakly because we've seen the token Mr. before. On ers, so just to note, when the present token, and so far none of these have had logit effects, which is interesting. When the present token is this D, the attention is on ers because we've seen this pattern before, and the logit effect is ers. When the present token is ers, the attention's on li because we've seen this before, and the logit effect is li. Then we move to li, attention is on this comma. We move to was, attention is on the beginning. Induction head example 2. Ters, the, pot, ters, period, arrived, had, away, semicolon, okay. Raw attention pattern and logit effect for the induction head, 1-8, on some segments of the first paragraph of Harry Potter and the Philosopher's Stone. The logit effect value shown is the effect of the result vector for the present token on the logit for the next token. Unembed weights, output weights H, result H, present token, next token, which is equivalent to running the full output value circuit and inspecting the logit this head contributes to the next token. Earlier, we promised to show induction heads on more tokens in order to better test our theory of them. We can now do this. Given that we believe induction heads are attending to previous copies of the token and shifting forward, they should be able to do this on totally random repeated patterns. This is likely the hardest test one can give them, since they can't rely on normal statistics about which tokens typically come after other tokens. Since the tokens are uniformly sampled random tokens from our vocabulary, we represent the nth token in our vocabulary as n, with the exception of the special token start. Notice that this is totally off distribution. Induction heads can operate on wildly different distributions as long as the more abstract property that repeated sequences are more likely to reoccur holds. Here we see the attention pattern, not much activation. Then here, see high activation. As in our previous attention pattern diagram, this diagram shows the value-weighted attention pattern for various heads, with each head involved in K composition colored by our theory. Attention heads are shown acting on a random sequence of tokens, repeated 3 times, and denotes the nth token in our vocabulary. This seems like pretty strong evidence that our hypothesis of induction heads is right. We now know what K composition is used for in our 2-layer model. The question now is how K composition accomplishes it. How induction heads work. The central trick to induction heads is that the key is computed from tokens shifted 1 token back. The query searches for similar key vectors, but because keys are shifted, finds the next token. The following example, from a larger model with more sophisticated induction heads, is a useful illustration. So here we see the attention's on pot, attention pattern moves, information, ters, and that key, pot, the logic effect is ters, pot, attention on the, and the query is pot. Query key circuits can be expanded in terms of tokens instead of attention heads. Above, key and query intensity represent the amount each token increases the attention score. Logic effect is the output value circuit. The minimal way to create an induction head is to use K composition with the previous token head to shift the key vector forward 1 token. This creates a term of the form identity AH negative or AH minus 1 weights in the query key circuit, where AH minus 1 denotes an attention pattern attending to the previous token. If weights matches cases where the tokens are the same, the query key version of a copying matrix, then this term will increase attention scores when the previous token before the source position is the same as the destination token. Induction heads can be more complicated than this. For example, other 2-layer models will develop an attention head that attends a bit further than the previous token, presumably to create an AH-1, AH-2 weight term so some heads can match back further. Checking the mechanistic theory. Our mechanistic theory suggestions that induction heads must do 2 things. Have a copying output value circuit matrix, have a same matching query key circuit matrix associated with the identity, attention on H-1, weights term. Although we're not confident that the eigenvalue summary statistic from the detecting copying section is the best possible summary statistic for detecting copying or matching matrices, we've chosen to use it as a working formalization. If we think of our attention heads as points in a 2D space of query key and output value eigenvalue positivity, all the induction heads turn out to be in an extreme right-hand corner. Second layer attention heads by output value and query key eigenvalue positivity. All the induction heads are the extreme of output value and query key positivity. Makes sense? One might wonder if this observation is circular. We originally looked at these attention heads because they had larger than random chance K composition, and now we've come back to look in part at the K composition term. But in this case, we're finding that the K composition creates a matrix that is extremely biased towards positive eigenvalues. There wasn't any reason to suggest that a large K composition would imply a positive K composition, nor any reason for all the output value circuits to be positive. But that is exactly what we expect if the algorithm implemented is the described algorithm for implementing induction. term importance analysis. Earlier, we decided to ignore all the virtual attention head terms because we didn't observe any significant V composition. While that seems like it's probably right, there's ways we could be mistaken. In particular, it could be the case that while every individual virtual attention head wasn't important, they matter in aggregate. This section will describe an approach to double-checking this using ablations. Ordinarily, when we ablate something in a neural network, we're ablating something that's explicitly represented in the activations. We can simply multiply it by 0 and we're done. But in this case, we're trying to ablate an implicit term that only exists if you expand out the equations. We could do this by trying to run the version of a transformer described in our equations, but that would be horribly slow and get exponentially worse as we consider deeper models. But it turns out there's an algorithm which can determine the marginal effect of ablating the nth order terms, that is, the terms corresponding to paths through V composition of n attention heads. The key trick is to run the model multiple times, replacing the present activations with activations from previous times you ran the model. This allows one to limit the depth of path, ablating all terms of order greater than that. Then by taking differences between the observed losses for each ablation, we can get the marginal effect of the nth order terms. Algorithm for measuring marginal loss reduction of nth order terms. Step 1. Run model, save all attention patterns. Step 2. Run model, forcing all attention patterns to be the version you recorded, and instead of adding attention head outputs to residual stream, save the output, and then replace it with a zero tensor of the same shape. Record resulting loss. Step N. Run model, forcing all attention patterns to be the version you recorded, and instead of adding attention head outputs to residual stream, save the output and replace it with the value you saved for this head last time. Record resulting loss. Note that freezing the attention patterns to ground truth is what makes this ablation only target V composition. Although this is in some ways the simplest algorithm, focused on the output value circuit, variants of this algorithm could also be used to isolate Q or K composition. As the V composition results suggested, the second order virtual attention head terms have a pretty small marginal effect in this model, although they may very well be more important in other, especially larger models. So here we see type, example, equation, and marginal loss reduction. For type direct path, order 0, this is just a straight line. Equation, unembedding weights, embedding weights. Marginal loss reduction, 1.8 nats, relative to uniform predictions. Negative 1.8 nats over one term. Type individual attention head order 1. So here we see the data flow into the attention head, and then out. Attention H, product, unembedding weights, output value weights H, embedding weights, marginal loss reduction, minus 5.2 nats, relative to only using direct path. Virtual attention head, order 2. See the diagram as it moves through. Attention H2, attention H1, product, unembedding weights, output value weights H2, output value weights H1, embedding weights, marginal loss reduction, minus 0.3 nats, relative to only using above. We conclude that for understanding two-layer attention-only models, we shouldn't prioritize understanding the second-order virtual attention heads, but instead focus on the direct path, which can contribute to bigram statistics and individual attention head terms. We emphasize that this says nothing about Q and K composition, higher-order terms in the output value circuit not mattering, only rules out V composition as important. Q and K composition correspond to terms in the QK or query key circuits of each head instead. We can further subdivide these individual attention head terms into those in layer 1 and layer 2. So here we see layer 1 attention heads, marginal loss reduction, minus 0.5 nats, minus 1.3 nats, notes, relatively small effect, but keep in mind these heads also contribute to layer 2 query key circuits, and then layer 2 attention heads, minus 4 nats, minus 5.2 nats. We'll focus on these. Much larger effect. These heads are a lot more sophisticated than the layer 1 heads, since they can use layer 1 heads in their query key circuits. This suggests we should focus on the second layer head terms, virtual attention heads. Although virtual heads turned out to be fairly unimportant for understanding the performance of the two-layer model, we speculate that these may be much more important in larger and more complex transformers. We're also struck by them because they seem theoretically very elegant. Recall that virtual attention heads were the terms of the form attention H2, attention H1, product OV weights H2, OV weights H1 in the path expansion of the Elhage equation, corresponding to the V composition of two heads, where Q and K composition affect the attention pattern. V composition creates these terms which really operate as a kind of independent unit which performs one head operation and then the other. This resulting object really is best thought of as the composition of the heads, H2 and H1. It has its own attention pattern, A of H2 and H1, AH2, AH1, and its own output value matrix, output value weights H2 and H1 equals output value weights H2, output value weights H1. In deeper models, one could in principle have higher order virtual attention heads, e.g. H3 and H2 and H1. There are two things worth noting regarding virtual attention heads. Firstly, this kind of composition seems quite powerful. We often see heads whose attention pattern attends to the previous token, but not heads who attend two tokens back. This may be because any useful predictive power from the token 2 back is gained via virtual heads. Attention patterns can also implement more abstract things, such as attending to the start of the current clause or the subject of the sentence. Composition enables functions such as attend to the subject of the previous clause. Secondly, there are a lot of virtual attention heads. The number of normal heads grows linearly in the number of layers, while the number of virtual heads based on the composition of two heads grows quadratically. On three heads grows cubically, etc. This means the model may, in theory, have a lot more space to gain useful predictive power via the virtual attention heads. This is particularly important because normal attention heads are, in some sense, large. The head has a single attention pattern, determining which source tokens it attends to, and D-head dimensions to copy from the source to destination token. This makes it unwieldy to use for intuitively small tasks where not much information needs to be conveyed, e.g. attending to previous pronouns to determine whether the text is in first, second, or third person, or attending to tense markers to detect whether the text is in past, present, or future text. Where does this leave us? Over the last few sections, we've made progress on understanding one-layer and two-layer attention-only transformers, but our ultimate goal is to understand transformers in general. Has this work actually brought us any closer? Do these special, limited cases actually shed light on the general problem? We'll explore this issue in follow-up work, but our general sense is that yes, these methods can be used to understand portions of general transformers, including large language models. One reason is that normal transformers contain some circuits which appear to be primarily attentional. Even in the presence of MLP layers, attention heads still operate on the residual stream and can still interact directly with each other and with the embeddings. And in practice, we find instances of interpretable circuits involving only attention heads and the embeddings. Although we may not be able to understand the entire model, we're very well positioned to reverse engineer these portions. In fact, we actually see some analogous attention heads and circuits in large models to those we analyzed in these toy models. In particular, we'll find that large models form many induction heads, and that the basic building block of their construction is K composition with a previous token head, just as we saw here. This appears to be a central driver of in-context learning in language models of all sizes, a topic we'll discuss in our next paper. That said, we can probably only understand a small portion of language models in this way. For one thing, MLP layers make up 2/3 of a standard transformer's parameters. Clearly, there are large parts of a model's behaviors we won't understand without engaging with those parameters. And in fact, the situation is likely worse. Because many attention heads interact with MLP layers, the fraction of parameters we can understand without considering MLP layers is even smaller than 1/3. More complete understanding will require progress on MLP layers. At a mechanistic level, Their circuits actually have a very nice mathematical structure. See additional intuition. However, the clearest path forward would require individually interpretable neurons, which we've had limited success finding. Ultimately, our goal in this initial paper is simply to establish a foothold for future efforts on this problem. Much future work remains to be done. So here, I'll just skim through this related work, see work on circuits, similar circuits approach, rethought, okay, interesting. It's possible that circuit analysis, we've noticed several interesting high-level differences between the original circuits work and studying circuits in attention-only transformer language models. It's possible that circuit analysis of attention-only models scales very differently with model size. In an attention-only model, parameters are arranged in comparatively large, meaningful, largely linear operating chunks corresponding to attention heads. This creates lots of opportunities to roughly understand quite large numbers of parameters. Even very large models only have a few thousand attention heads. A scale where looking at every single one seems plausible. Of course, once one adds MLP layers, the majority of parameters are inside of them, and this becomes a smaller relative win for understanding models. I've had a lot more success studying circuits in tiny attention-only transformers than we did with attempting to study circuits in small vision models. In small vision models, the problem is that neurons often aren't interpretable. Nothing analogous seems to happen here, since we can reduce everything into end-to-end terms. However, perhaps when we study models with MLP layers, which can't be reduced into end-to-end terms, more closely, we'll also find that scale is needed to make neurons interpretable. LogicLens, previous work by Lesrong on nostalgia based on a method they called LogicLens, explores the same linear structure of the residual stream heavily exploited. The LogicLens approach notes that since the residual stream is iteratively refined, one can apply the unembedding matrix to earlier stages of the residual stream, such to look at unembedding weights xi, to look at how model predictions evolve in some sense. Our approach could be seen as making a similar observation, but deciding that the residual stream isn't actually the fundamental object to study. Since it's the sum of linear projections of many attention heads and neurons, it's natural to simply multiply out the weights to look at how all the different parts contributing to the sum connect to logits. One can then continue to exploit linear structure and try to push linearity as far back into the model as possible, which roughly brings one to our approach. Attention head analysis. Work follows the lead of several previous papers, investigating transformer attention heads, attention patterns, visualizations, quickly expanded on. The largest difference between these previous analyses of attention heads and our work really seems to be a matter of goals. We seek to provide an end-to-end mechanistic account rather than empirically describe attention patterns. We only study very small toy models, and only really then to illustrate and support our theory. Finally, we focus on autoregressive transformers rather than denoising model like BERT. Our investigations benefit from these previous papers. Like most of these papers, we observe the existence of a previous token attention head in most models. Sometimes in small models, we get an attention head that's more smeared out over the last 2 or 3 tokens instead. We mirror other findings that many attention heads appear to use punctuation or special tokens as a default. Induction heads provide a concrete example of this. We find scaling attention patterns by the magnitude of value vectors to be very helpful for clarifying this. The toy models discussed in this paper do not exhibit the sophisticated grammatical attention heads described by some of this prior work. We do find more similar attention heads in larger models. Describe attention heads, which preferentially attend to rare tokens. We wonder if those might be similar to the skip trigram attention heads we describe. Several papers note the existence of attention heads which attend to previous references to the present token. It occurs to us that what we call an induction head might appear like this in a bidirectional model trained on mass data rather than an autoregressive model. The mechanistic signature would be attention on H-prev, attention H-prev, weight, and a query key expansion with large positive eigenvalues. Criticism of attention as explanation. An important line of work criticizes the naive interpretation of attention weights as describing how important a given token is in affecting the model's output. Our framework might be thought of as offering, for the limited case of attention-only models, a typology of ways in which naive interpretation of attention patterns can be misleading, and a special way in which they can be correct. When attention heads act in isolation, corresponding to the first-order terms in our equations, they are indeed straightforwardly interpretable. In fact, it's even better than that. As we saw for the one-layer model, we can also easily describe how these first-order terms affect the logits. However, There are three ways that attention heads can interact: query, key, and value composition, to produce more complex behavior that doesn't map well to naive interpretation of the attention patterns, corresponding to an explosion of higher order terms in the path expansion for the transformer. The question is how important these higher order terms are. We've observed cases where they seem very important. Induction heads offer an object lesson in how naive interpretation of attention patterns can both be very informative and also misleading. On the one hand, attention pattern of an induction head itself is very informative. In fact, for a non-trivial number of tokens, model behavior can be explained as an induction head attended to this previous token and predicted it was going to reoccur. But the induction heads we found are totally reliant on a previous token head in the prior layer through K composition in order to determine where to attend. Without understanding the K composition effect, one would totally misunderstand the role of the previous token head and also miss out on a deeper understanding of how the induction head decides where to attend. This might also be a useful test case for thinking about gradient-based attribution methods. If an induction head confidently attends somewhere, its softmax will be saturated, leading to a small gradient on the key, and thus low attribution to the corresponding token, obscuring the crucial role of the token preceding the one that attends it. How much more is left? Okay, I'll go down to here. So, Bertology generally. The research on attention heads mentioned above is often grouped in a larger body of work called Bertology, which studies the internal representations of transformer language model representations, especially BERT. Besides the analysis of attention heads, Bertology research has several strands of inquiry. Likely the largest is the line of work using probing methods to explore the linguistic properties at various stages of BERT's residual stream, referred to as embeddings in that literature. Unfortunately, we'd be unable to do justice to the full scope of Bertology here, and instead refer readers to this review. Our work in this paper primarily intersected with the attention head analysis aspects of Bertology for a few reasons, including our focus on attention-only models, our decision to avoid directly investigating the residual stream, and our focus on mechanistic over top-down probing approaches. Mathematical framework. Our work leverages a number of mathematical observations about transformers to reverse engineer them. For the most part, these mathematical observations aren't in themselves novel. Many of them have been implicitly or explicitly noted by prior work. The most striking example of this is likely Dong et al., who considers paths through a self-attention network in their analysis of the expressivity of transformers, deriving the same structure we find in our path expansion of logits. Many examples include a multi-way Einsums description of multi-headed attention, which might be seen as another expression of same tensor structure we've tried to highlight in attention heads. Even in cases where we aren't aware of papers observing mathematical structure we mention, we'd assume that they're known to some of the researchers deeply engaged in thinking about transformers. Instead, we think our contribution here is in leveraging this type of thinking to mechanistic interpretability of models. Other interpretability directions. There are many additional approaches to NN interpretability, including interpreting individual neurons, influence functions, saliency maps, feature visualization. Interpretability interfaces. It seems to us that interpretability research is deeply linked with visualizations and interactive interfaces supporting model exploration. Without visualizations, one is forced to rely on summary statistics, and understanding something as complicated as an NN in such a low-dimensional way is very limiting. The right interfaces can allow researchers to rapidly explore various kinds of high-dimensional structure, examine intention patterns, activations, model weights, and more. When used to ask the right questions, interfaces support both exploration and rigor. ML has a rich history of using visualizations and interactive interfaces to explore models. This is continued in the context of transformers, especially with visualizations of attention. Recent architectural changes. Some recent proposed improvements to the transformer architecture have interesting interpretations from the perspective of our framework and findings. Primer. Primer is a transformer architecture discovered through automated architecture search for more efficient transformer variants. The authors isolate two key changes, one which is to perform a depthwise convolution over the last three spatial positions in computing keys, queries, and value vectors. We observe that this change would make induction heads possible to express without K composition. Talking heads attention is a recent proposal which can be a bit tricky to understand. An alternative way to frame it is that where regular transformer attention heads have output value weights H equals output weights H, value weights H. Talking attention heads effectively does output value weights H equals alpha 1 H, output weights 1, value weights 1, plus alpha 2 H, output weights 2, value weights 2. And the same thing for the query key weights. This means that the output value and query key matrices of different attention heads can share components. If you believe that, say, multiple copying heads could share part of their output value matrix, this becomes natural. This is just follow-up stuff. Okay. Well, we made it through. Took 2 hours. I am not going to get to the 5 remaining papers that I plan to read right now, but I still plan to read them in the near future. So I'll make videos on those, maybe separately, maybe grouped, depending on how long they all tend to be. Another reason I'm not going to continue right now is because I know that Neel Nanda made a video explaining this paper. I think it's like 2.5 hours or something like that. And rather than just speed run through a bunch of these, especially because this is so math heavy, I'm going to go watch that video and try to soak it up more, maybe take notes, think about it. Yeah. So this was cool though. It's really interesting, especially the visualizations. They're fun to play with. I'm definitely going to check out some of the recommended visualization papers and libraries that they linked and tutorials maybe down here. Peace.